Let's look at this problem. The statement of this problem is quite simple, huh? But it doesn't necessarily mean that the question itself is simple. It looks like this is a number theory problem. So let's read it. So it's asking about the 10th digit of this large exponential number. Okay, so, and the keyword is 10th digit. So normally when we do the number theory practice, there are a lot of questions about the singles digit, especially the singles digit of an exponential. The 10th digit can be a little bit hard. So the straightforward way is that we follow the same trick and we calculate some lower exponentials of 7 and then try to find if there is any pattern or cycles or something like that. Okay, let's start from there. So actually, you know what? I think of another method to solve this. Okay, let's try that next. Okay, let's call the first method 1. Let's try some lower exponentials of 7. So 7 to 1, we know that the first two digits is 0, 7. The 10th is 0, right? And 7 to 2, that's 49. 7 to 3, that's 7 times 49, right? So 7 times 9, that's 63, and it's 343. And this one, 7 to 4th, will be, that will be a much larger number, so let's try that, right? That's 21, I'll put 2 here. So 4, 7, that's 28, so that's 30, and that's 21, 24. So this is 2401. So are there any patterns here already? 0, 4, 3, 0. Not much, huh? But actually we like this. 0, 1. So 7 times 0, 1. There is a pattern here. All right. So let's check 7 to the 5th. So then it's it equals to 2401 times 7. So the last two digits got to be 7 and 0. So see the cycle? All right, so the period of this is certainly 4. Beautiful. It's something like the 1st digit. Since the cycle is 4, so the 10th digit repeats itself every 4th power. So we can write 2011. That is not divisible by 4. So, but we know 2008 is divisible by 4. So these two numbers is divisible by 4, so the whole number is divisible by 4. So this one would equal to 3 when we mod 4. So this notation is just another way to write that when we divide 2011 by 4, we have something and the remainder is 3. All right. So let's come back to this cycle. So that's 3, right? So every 4 exponentials. Then the remainder is 3, then it's this. Therefore, the 10th digit of this large exponential number is D, 4. Okay, let me introduce the second methodology. What I find while I read this problem is that I notice one thing, that 7 squared equals to 49. So a good thing about this is that equals to 50 minus 1. All right, so we like the 10th. So any exponentials of these 10s will just give more zeros at the end, right? So, and then that minus 1. Beautiful. I like it. But however, this 2011 is not an even number. So we can do this. 7 to 2011, we rewrite this as 7 to 2010. That'll be an even number, then times 7. Alright, then we can rewrite this as, that's by the exponential rule, that equals to 7 squared to 10 1005, then times 7. Beautiful. So that's 49 1005 times 7. All right, let's use this observation. So 50 minus 1 1005 times 7. Beautiful. So we can do a binomial expansion on this exponential, right? So the higher powers will just have a lot of zeros on the ones and on the tens and the hundreds and so on and so forth. So we just pay attention to the last few items, right? So we know that the exponential is 1005, so there got to be 1005 plus 1 terms when we expand this by binomial expansion. Therefore, we just look at the last 2 terms. So there are 1006 terms, and we know that this is a negative sign. So we know that there is a pattern of this negative sign when you do this binomial expansion. The first is positive, right? And the negative, positive, negative, and positive and negative, so on and so forth. And this is an even number. The sign of the last term got to be a negative sign. So this got to equal to something times 7. So the last term is minus 1, because 1 to 1005, that's still 1. Then what's the second last? That'll be 1005, choose 1, and times 50, right? And plus dot dot dot. There are a lot of terms here. Since all of the terms here are the number 50 to the power of 2 or greater, right? So then the last 2 digits got to be both zeros. The tens and the ones digits are both zeros, so they will not affect our final results. All right, so let's just ignore those. Okay, so let's see. So this term will just equal to, we have some dot 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 plus 1005 times 50 minus 1 times 7. So that equals to dot 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 plus, look at this. That's 1000 plus 5, right? 1000 times 50, that's again a lot of zeros at the end, so we ignore those. So that's just 5 times 50 minus 1 times 7. So again, this is dot 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 plus 250, right? Minus 1 times 7. And that is some dot dot. So we can use modular algebra in here to make it more rigorous. But in here, for simplicity, for this problem, not necessary. So let's continue the calculation. So that minus that, the last 2 digits will be 49, right? Times 7. We can ignore all these numbers, which just supply a lot of zeros at the 10th digit and the 1st digit. And 49 times 7. Okay, so let's come to the top. So 49 times 7. All right, so that equals to 7 times 9, that's 63. And 4 times 7, that's 28. Then that will be 34. Beautiful. So the 10th digit is 4. We can compare that to this. So the answer is D, 4. If you like this video, please subscribe and thumb up. If you have questions, please comment.